Hi, welcome back to es346 Basic Thermodynamics. This is Module 4.5, Solid Liquid Specific Heat, and the section of the textbook is also Section 4.5. Here are the two learning objectives for this module. At the end of the module, you will understand the specific heat behavior of solids and liquids, and you'll be able to calculate the energy requirements for heating or cooling of solids and liquids. So I want to talk about specific heat, but now for incompressible materials. And so something that's incompressible, what we mean is that the volume does not change as we exert a pressure on it. In solids and liquids, that tends to be true. For most changes in pressure, you don't really change what their volume is. And I want to remind you that H is defined as U plus PV. And so if I was to go ahead and take the temperature differential of this, so I'm going to make this dH dt equal to du dt plus, now I've got ddt of PV, so I'm going to have P dV dt plus V dP dt. All right. So looking at this, if I was doing something at constant pressure, so imagine I had, a brick, and I wanted to know how much heat it took to go ahead and heat up a particular delta T. And if my brick was just sitting there, this would be a constant pressure process. And so what that means is that this term over here is zero, because there's no change in pressure. Now also, my brick really doesn't change much in volume. It's very, very small. Its thermal expansion coefficient is pretty small. So this dV dt term is also zero. So what I'm left with in this equation is dH dt is du dt, which is just saying that Cp is equal to Cv. So the heat capacity for solids and liquids, or anything that's incompressible, Cp and Cv, the values are essentially the same, and sometimes they're just reported as simply C, or as Cp. You can get these values from table A3, and we're looking at table A3A here. And so we've got a list of materials, and what is assumed here is that these are all liquids and solids, so they're incompressible. In fact, there's even some fluids, it looks like, in this list. And I'm looking over at the very last column where we have the specific heat. And so, for example, we'll do an example here in a minute where we're looking at water, and we look at our heat capacity values. They change a little over temperature as it stays in the liquid form from 0 to 100, but it's all about 4.2. So here's the example that I want to solve. We've got a swimming pool. It's 8 feet deep, and it's absorbing solar energy at a rate of 300 watts per square meter. And we want to know what's the temperature change in the water after 4 hours. So let's go ahead and draw up our swimming pool here. And it's absorbing heat from the sun. And it's 8 feet deep. And what we want to know is what's the temperature change. And so it gives us the rate of heat is coming in per square meter. So it's kind of like we just take a little section here, and we're looking at that. So we're going to do our energy balance over there. So let's write our first of all energy balance for that. Delta U is the energy that goes in, which is Q. And it's not doing any work. It's not expanding. This is an incompressible material. So delta U is Q, and we can write that down as MC delta T. And we're given Q at a rate. This is watts per square meter. And so this is actually, we're going to keep this as Q dot times T. So square meter, so we'll go ahead and just take 1 square meter of material that's 8 feet deep, and that's going to go ahead and be our control mass. So remember, as I said, the heat capacity, Cp, is essentially the same as Cv, and I'm just calling it C here in this example. So my first energy balance is the mass times the heat capacity times delta T, which is what I'm trying to solve for, is equal to Q dot times the time. Q dot is the energy, that's 300 watts per square meter that's coming in. And I need the mass, and I'm given a volume. So remember that the mass is equal to the density times the volume. And in fact, if I go back to that previous slide, this column right here is density. The density of water is close enough. I'm going to say that it's about 1,000 kilograms per cubic meter, and that'll be close enough for this problem here. So let's come back over here, and so I'm going to put down in place of mass, I'm going to do rho v. So 1,000 kilograms per cubic meter, and the volume is, well, I've got 1 square meter and then I have 8 feet deep, and I need to do a conversion factor that there is 3.281 feet per 1 meter. So those two terms combined together give me my volume. And now the heat capacity, which was about 4.18 in the previous table, and delta T, which is what we're solving for, and that's going to be equal to this Q dot times time by 300, and I've got watts coming in that square meter, and the time is, we have 4 hours. Now watts is a joule per second, so I need to get this, change this hours into seconds, and so we're going to have 3,600 seconds per hour. And if I looked at my values of CP, so I'm going to go back to that previous table real quick to make this clear. If we look at it over there, those units are kilojoules per kilogram Kelvin. So we've got kilojoules there. Over here, watts, which is a joule per second. So I'm going to go ahead and need to divide all of that by 1,000 watts per kilowatt. And now I'm going to go ahead and solve this equation right here for delta T. And if I do that arithmetic, delta T is about 0.42 degrees Celsius. So not a lot. 300 watts per square meter, that's a typical sunny day in a temperate climate. 4 hours seems like a long time, but 8 feet is a pretty deep pool, and heat capacity of water is pretty high. It's actually one of the larger of most materials. All right, I want to look at another incompressible material in an important energy balance, and it deals with the energy required to pump fluids. And this is really important for engineers. And so first I'm going to go ahead and derive a simple equation from this. And again, I'm going to start with what we often start with, which is our definition of enthalpy, which is U plus PV. And what I'm going to do now is take a differential form of this. So I've got the dH is equal to du plus PV plus VP. And now what we want to do is we're looking at, we've got an incompressible material. So effectively, our volume is equal to 0. And so du, well, this is the change in internal energy for a incompressible material, which was CV dt. And usually when you pump things, there's really not much change in the temperature. So that's effectively equal to 0. So what we're left now with is our change in enthalpy is VdP. Now for pumping, dP can be pretty large. And so it actually turns out if I want to know the energy requirement in order to pump a fluid, I'm going to go ahead and want to integrate V dP, and if it's incompressible, the volume I can take out of that integral, and this ends up being equal to V delta P. And that's the amount of energy required to pump a fluid. All right, let's go ahead and do an example here. And the question asks, I've got water, and it's pumped from 0 to 1,000 psi gauge, and it's coming at a rate of 5 gallons a minute. And we want to know is, what's the power requirement in kilowatts? So we just saw from the previous slide, if I want to know what that work requirement is, that's going to end up being equal to delta H, which is equal to V delta P. And per time, this will be a V dot electrical watt. Those are all per time. So what I want to know is what my volume rate is over the pressure. So let's go ahead and write down, we've got 5 gallons a minute. So 5 gallons per minute. And we're going to want this in kilowatts, which is a kilojoule per second. So we want this per second. So do a unit conversion here. 1 minute is 60 seconds. So there's my volume flow rate. But I've got this in gallons. Let's get this into normal SI units, which is going to be cubic meters. So I've got a conversion factor in the book that's 1 cubic meter is equal to 264 gallons. And that's going to cancel out my gallons. My minutes are canceling. So now I've got cubic meters per second. So now I just need to put in my pressure change of 1,000 PSIG. And kilowatts, we call that a kilojoule is a kilopascal times a meter cubed. So I want to go ahead and get my PSI into kPa. So I'm going to do a conversion factor here of 101 kPa is 14.7 psi. And now my units should cancel. My PSIs are going to cancel there. We've got a kPa, meter cubed per second. That's going to go ahead and give me kilowatts. So let's just go ahead and do that arithmetic there, and that's about 2.17 kilowatts. So we realize that's not an inconsequential amount of energy. And so you really need to make sure you include this term in your energy balance. Otherwise, you kind of throw the baby out with the bathwater.